section 4.1 through 4.3. We'll start with 4.1. Chapter 4 is actually, you're going to find that it's we're going to rethink about a lot of things that we've actually thought about before, using sometimes a little bit different words and some bigger overarching ideas. But a lot of the times it's going to come down to doing the same things and the same words and the same notions that we've talked about before. That is a linear independence, linear dependence, a spanning set, and a change of basis, or a basis and coordinate systems. So all of these things we're going to think about, but coming at it from a slightly different, bigger picture angle, and that's what we start talking about in chapter 4.1, which is this idea of what we call a vector space. So a vector space. So far we've thought about vectors, and vectors for us have been simply lists of numbers, right? So something in R6 or R10 or R2 or R3, that's a vector. But we're going to take a step back and abstract it just a little bit for now, and I'm going to give a formal definition, and we'll look at a bunch of examples of what I mean by a vector space. Definition: a vector space is a set V, so it's just a set of objects. So for Rn, that's the lists of numbers. It's a set V with two operations, which we'll call addition and scaling. So addition plus and scaling we'll call dot times for now, and we'll see how that works, such that a whole bunch of things are true. One, if V1 and V2, we're going to still write them as vectors as before, with this same notation. So if V1 and V2 are in the set V, then so is V1 plus V2, but also scaled any way we like. So C1 V1 plus C2 V2 for any C1 and C2 in R. So we're going to be able to scale by any real number and still stay in the set, and we're going to be able to add up vectors that were in the set and stay in the set. So remember from our language from before, that's the same thing as saying that it's closed under addition and closed under scalar multiplication. So we start with two things in the set, we add them up, it's just something else that's in the set. We scale, we start with something in the set, we scale it, it's still in the set. Okay. Okay, and so we're going to have a couple of other technical requirements as well. Actually, a bunch of them. I'm going to write them down once, but then most of the time we'll just be able to ignore these requirements. Two, so there is a vector 0 in V for which V plus 0 is 0 plus V is V for all V. Right, so there's just a special 0 vector. And again, we're going to look at a bunch of more examples of different vector spaces other than just Rn and see how these things all apply. 3, U plus V is V plus U. So I can add in either order and I get the same thing. 4, we can associate, so this is an associative rule. U plus V plus W is U plus V plus W. 5, we can associate with scaling. C2 times the vector V then times C1 is the same thing as C1, C2 times the vector V. So everything that we expect to happen has got to happen, so there's no tricks here. right? So 6c times u plus v is cu plus cv. So we can distribute a scale. This is a scalar. We can distribute it to a vector just as if we want. Notice that we never talk about u times v for two vectors. We can't multiply vectors. For two vectors in Rn, we never multiply them. We dot them sometimes when we get a real number back, but that's not a multiplication of vectors because it doesn't return another vector. There is a cross product only in R3, but it doesn't work in general vectors. So we don't really have a multiplication. Also, so 0 times any vector v is the 0 vector. And finally, 1 times any vector v is just the vector v. So, lots of technical things which just say that everything works the way that we want it to work. The algebra of vectors has to work the way we want it to work. In general, we're going to think about a vector space as a set where we can add stuff up and scale it as well. So let's look at some examples of those things. And we'll start with the one that we already know. So if v is just Rn. So if v is Rn, we can add vectors together in Rn. We already know. We get another vector in Rn. We can scale them. We get another vector in Rn. Here's another one. All right, so this is a different notation. This is a script P, or a block P, and we're going to call this P sub n. And what this is all nth degree polynomials. Right, if I have two 10th degree polynomials and I add them up, I get another 10th degree polynomial. So I can add two polynomials together and it stays and the degree doesn't change. If I take a 10th degree polynomial and I scale it by any constant, I multiply by 6 or -4 or 32, the degree of the polynomial doesn't change. So by adding, I stay within all specific degree polynomial, and by scaling, I also stay within all specific degree polynomials. So these polynomials are, in fact, a vector space. I can look at all infinite sequences of real numbers. Right, so for example, a small vector in this case might be, here's an infinite sequence of real numbers. But it goes on forever. Right? But I could add up two of those things. If I had two different infinite sequences of real numbers, there's a pretty obvious addition. Just add up piece by piece, component by component. And I can also scale the whole thing, and I get an infinite sequence of real numbers. So we have a set, we have an addition, and we have a scaling. And those things together make for a vector space. I can look at the set of all 3 by 3 matrices, and in fact it doesn't have to be 3. I could say 6 by 6 or 10 by 10 as long as I had square matrices. We can add them up, right? So addition works just like we'd like it to, and we can scale. So both of those things work. And all of those algebra properties are also satisfied. Subspace. So I'm going to give a formal definition, and then we're going to look at how that applies to real situations in terms of Rn, and then R2 and R3, some of our favorite spaces where we can draw pictures. So a subspace, definition. A subspace of Rn is a subset, let's call it H, for which the following is true. The zero vector is in H. So all I'm doing is picking out a whole bunch of vectors. In order for it to be a subspace, one of those vectors that I pick out has to be the zero vector. 2, if x and y are in H, then so is x plus y. So if I have any vectors that are in the set that I start with, and then I add them up, then the resulting vector that I get, x plus y, also has to be there. And then finally, if x is in H, then any scaled version of x is also in H. Then Cx is in H for all C real numbers. All right, so we have a couple of, so what we say here is this is, we say that H is closed under addition and scaling. So when I say that a set is closed under some operation, I mean that if I apply the operation to things that are in the set, it stays in the set. So let's look at some things that are subspaces and some things that aren't subspaces. So this is some examples of different things. So here's R2. Let's look at this line. All right, so this line is a subset of R2, but it's not a subspace, first of all, because it doesn't include the zero vector. So if this is H, if H is the line, then 0 is not in H, so H is not a subspace. All right. What if I made a line that did include 0? Here's R2. What if I looked at all vectors that are on this line? Well, now 0 is in there, so that's good. The 0 vector is there. If I have two vectors that are on this line, if I take vector v1, which is on the line, and I take vector v2, which is also on the line, and I add them up, well, what happens? Remember, when I add vectors, but then v1 plus v2, I take the whole vector v2 and attach it to the end of v1, and it would still be on the line. So by adding up two vectors that are on this straight line, they get another vector which is still on that same line. So this one is closed under addition. That is, if I add two vectors, it stays on the line. It's also clearly closed under scaling. If I take vector v1 and I scale it by anything, positive or negative, to turn it into the other direction, then it still stays on the line. So it's also closed under scaling. So yes, it is a subspace. Let's say that H is the first quadrant. Is that a subspace? And let's include everything on the axes in the first quadrant as well. So that it does include the 0 vector. So 0 vectors in there. If I take two vectors which point in the first quadrant and I add them up, well, the vector that I get back is still in the first quadrant. So 0 is in H, and it's closed under addition. That is, if I add up two vectors that are in the set, it stays in the set. However, it is not closed under scaling. If I took this vector and I scaled it, it feels like it stays in the first quadrant, but that scaling has got to be true for any real number, positive or negative. If I scale one of these vectors by a negative value, well, that turns it back into this quadrant, and that's not in H. But it isn't, so it is not closed under scaling by negatives. So it is not a subspace. So maybe you say, well, what if I look at not just the first quadrant? If the problem is closed under scaling and I need to include the negative scale versions, well, how about if we look at the first and third quadrants together? So let's say that H is first and third quadrants. Now zero's in H, and we've set it up so that it's closed under scaling. If I take a vector that's up here and I scale it by a positive number, well, it stays in the first quadrant. If I scale it by a negative number, well, that pushes it to the third quadrant, but since we've included the third quadrant, everything is good to go. So it's closed under scaling. However, it's not closed under addition, because if I take this vector, v1, well, let's call it w1, and I take this vector, w2, and I add them up, well, then it's over here. So by taking two vectors that are in the set and adding them up, it goes outside of the set. So it is not closed under addition. So it is not a subspace. I'm not going to prove this here, but here are some facts about subspaces of R2. There's only a few options. The set which only includes the zero vector, well, that's a subspace. Because if I take the set that only has the zero vector, well, it certainly has a zero vector. It's also closed under scaling, because if I scale 0 by anything, I get 0. It's also closed under addition, because if I add 0 plus 0, I still get 0. So that's a subspace. Another subspace is a line through the origin. We talked about that. The only other subspace is all of R2. We notice that if we try to include the first quadrant, it doesn't work because we would need to include the negative versions. But if I try to include the first and third, that doesn't work because by addition, I can get into the second quadrant. Similarly, I could get into the the fourth quadrant. And so as it turns out, if I include anything else other than just a straight line through the origin, in order to satisfy the definitions of a subspace, you need to include everything. And so these are the only subspaces of R2. And that's it. There are no other subspaces. For R3, we have a few other things. We still have the zero set, the set that just has the origin in it. That's a subspace. Even if we're in R3, a line through the origin is still okay. I can still scale it and it stays on the line. If I add up two vectors in the same direction, the resultant vector still points in the same direction. But because now we've added more space, we've got space to work with rather than just a plane, we have an analogous line through the origin that turns to a plane through the origin. Because if I have x, y, z, and I look at a plane that goes through the origin, so if I have a plane going through the origin and I add up two vectors that are on that plane, well, the resultant vector stays on the plane. If I scale to a vector that's on the plane, it still is on the plane. So a plane through the origin is, in fact, the subspace of R3. But after that, there's no other space to go. As soon as you move off of that plane, if you would, in order to satisfy the definitions, you've actually got to include everything. So these are the only subspaces of R3. We can talk about analogous situations for higher dimensions, but the words, we start losing words, and we have to talk about hyperplanes, which are essentially, a plane is a version of R2, if you want to think about it like that. It's a flat piece which only has two different directions to it. So in R4, we can talk about a subspace which has three possible directions to it. And we'll look at that a little bit more closely in the future. But these are all of the subspaces of R3. Let's start with a matrix and talk about some specific subspaces that come out of a given matrix. All right, so what we're going to look at now is what we're going to call the column space of a matrix. Okay, so given matrix A. The column space is the set of all linear combinations of its column vectors. All right, so I have a matrix, I have the vectors that make up its columns. If I look at all linear combinations, and we'll see that that is in fact a column space. So let me remind you what I mean even by linear combinations. So recall, if I have vectors v1 and v2 and v3, a linear combination of v1, v2, v3 is just an added up version where each of these might be scaled by different factors, by different scaling factors. Is C1 v1 plus C2 v2 plus C3 v3. That's a linear combination where C1, C2, and C3 can be anything I want them to be. Okay, so let's see, why is that in fact a subspace? If I take linear combinations of vectors, why is that a subspace? All right, so my claim is that for any set of vectors, v1 through vk, they might come from columns of a matrix. That's what we're looking at here. The column space of a matrix will be the linear combinations of its column vectors. But for any set of vectors, v1 through vk, the set of all linear combinations is in fact a subspace. That's my claim. So this is the set of all C1, V1 plus C2, V2 plus all the way to CK, VK. That's what we're looking at. But 0 is certainly in here because I'm allowed to dial these C1s and C2s to be anything I want. So I can set all of the C1s through CK to be 0. So if every C1 through CK is 0, well then that's a linear combination of these vectors, and I get the 0 vector back. 0, let's call this H. So the set of all linear combinations, let's call that H. Then 0 is in H because I can let C1 to be C2 to be all the way to CK. I can set them all to equal 0. If I took a vector that looked like this and I scaled it by anything, by 10, Well, then I'd simply scale each of those coefficients, scale each of those component pieces, and I'd still get a combination where I have a constant times v1, constant times v2, and so on, all added up. I'd get a linear combination of the vectors v1 through vk. So it's also clearly closed under scaling. So let's say C times C1 V1 all the way to CK VK is C times C1 V1 plus all the way to C CK VK. And the point here is that these things are all this is a linear combination of V1 through VK because I've just got a scale version of each of V1 through VK added up. I just changed the scale. It's also closed under addition. Because if I took two of these things, if I took C1 V1 plus all the way to CK VK, and I added this to another linear combination, let's call it D1 V1 all the way to DK VK. Then what I get is C1 plus D1 V1 plus all the way to CK plus DK VK. And that's another linear combination of V1 through VK. So it's closed under addition. And so in fact, all three of the definitions, pieces of a subspace are satisfied. I can say H is a subspace. Okay, subspaces. A subspace. We've already actually seen this word before in our understanding of Rn. We're going to look at it again a little bit more abstractly now. We've taken a step back to think about a vector space as an abstract object, which could take on a lot of different meanings. And we're going to look at all of these ideas in general and then remind ourselves how they worked in the Rn case as well. Remember, a subspace is really just a subset, which is also a vector space. That's a little different than we described it before, but that's really all that we need to think about it as a subspace. So a subspace of a vector space is just a subset where it's still closed under addition and it's still closed under scaling. That's what it means to be a subspace. Right, so closed under addition, scaling. And remember that closed means if I add two vectors up, it stays in the set. If I scale a vector, it stays in the set. Okay, so in R3, that's one of our favorite, is the XY plane a subspace? Well, the answer is yes. Because if I have R3, and I take two vectors that stay on the XY plane, and I add them up, it stays on the XY plane. And if I take a vector that's on the XY plane and I scale it, it stays on the XY plane. And that's really all that it takes in order to be a subspace. Closed under addition and closed under scaling. So is the unit circle in R2 a subspace? So here's R2, the XY plane. The unit circle is the circle here. If I looked at all vectors which stayed on the unit circle, does this form a subspace? Well, no, because if I add up any two vectors that are on the unit circle, it goes off of the unit circle. So no. It's not, or I could scale any of these vectors and it's no longer on the unit circle. It actually doesn't satisfy either of those. So it's not closed under addition or scaling. Let's say that V is P4. All fourth degree all fourth degree polynomials. Fourth degree polynomials. Let's say we have our question is H equal all polynomials with positive coefficients? Is that a subspace? Well, it is closed under addition, because if I take two fourth degree polynomials and add them up, if both of those polynomials have positive coefficients, then after I add them up, they still have positive coefficients. So it is closed under addition. And be careful, because it at first glance feels like it's closed under scaling as well. If I take a fourth degree polynomial with positive coefficients and I multiply by 6, well, then it still has positive coefficients. But be careful, because it has to be closed under scaling by any real number. Right, so it's not closed under scaling by negative numbers. If I take a fourth degree polynomial and I multiply by -6, well, if the original one had positive coefficients, the new one does not. So it has to be closed under any scaling, positive or negative, and also under any addition. So this is no. Here's another example of a subspace. So suppose that we started with R4 and we looked at, and let's let H be the span of a couple of vectors. Remember, a span is all linear combinations. That's what a span is. That's the definition of a span of some vectors. All linear combinations of the vectors. But that's by definition made to be a subspace, because if I have a linear combination of this, well, that's just a scaling times this and a scaling times this, and I add it up, well, then I still have a linear combination of those things. I've just changed the scaling factor. So really, span is created to be a subspace. And if I have the span of any set of vectors, then I will get a subspace of the original vector space. All right, that's what we got for 4.1. Next, we'll move into 4.2.